Ladies and gentlemen, welcome to the next lesson, which is on the network city, in which we calculate a different distance value using a street graph, the street graph. So in contrast to the grid city, where we used the Manhattan distance, so the x and y distance between two cells, we want to now use a more realistic geometry and compute the distances between parcels, between blocks, by using the street network. Therefore, open the file O2, Basic Urban Development Model. And after you opened it, you see this basic grasshopper file, in which you find on the right-hand side, so this bubble-shaped group. That's the simulation model that you already know from the grid city. That's exactly the same logic, the same dynamics. So I've changed nothing here. I've only changed the input to this model. And to use the model, we find at the top left side again the required plugins. So in this case it's the UMS plugin and the Anemone plugin, which we already have used in the grid city. In this case we need the decoding spaces plugin as well, which I provide you for download here on the website, but you also find it in the Food for Rhino repository. Okay, now this whole part is basically analyzing the distances between the individual parcels that we have in this setup. And this is a part of the city of Weimar. So you can see if I preview here the whole network, that's a part of Weimar, the street network. And I've just used a smaller sub area of the city, just because of shortening the computing time for the analysis and having a smooth example, so we don't need to wait for computing any kind of geometrical analysis. But you can extend this area to a larger one if you like. Okay, so in the first part we make some pre-processing, computing basically this or using the streets. Here the curve input, if we preview it, this is the green street network that you see here. That's our basic geometrical starting point. The blocks and the parcels are generated by the later script, so we feed these basic streets. So we created with this group the basic parcel structure. For this structure we compute in the end the area of each of the parcels and use this output for the further processing. What we do as well is that we connect the plots with the street network, and this is done. I'll just preview the outcome of it. So that's what we do. So we look for each plot, which of the street segments is the closest to the center point of the plot. And then we connect it with this line. So we connect each center point of the plot to the closest street segment. That's done with this first part of the script. And here with this component we computed these lines. And then we feed it back into, or we create a complete street network graph which contains the streets plus these small stubs, which goes into the parcels to connect the parcels to the network. That's what we have in this output, and this is then fed again into some kind of pre-structuring of our data that we have. So we have on the one hand side now the street network, and on the other hand side we have the list of parcels. So the street network is stored as a list of street segments and the parcels is stored as a list of polylines or surfaces. So these gray surfaces, these are our parcels. Later we will need to link these two data structures, because you remember the basic input for the grid city model or the dynamic urban simulation is the information about the distance between two blocks or two parcels in our case here. And this distance is what we need in our model in the next step as well. Therefore, we prepare the data structure with this pre-processing. Basically, in this output, we linked the sizes of the parcels to the next street segment. This is to give the street network analysis a weighting for the importance of a street segment for creating sources and origins of trips. So we assume that from bigger parcels there will be more people traveling from and to this parcel. That's the basic idea of this parcel weighting per street, which is then used as an input for the street network analysis components. So the whole part below, so the network analysis, that's something I don't explain in this lesson. This is introduced in the course on parametric urban design and analysis, and in the module computational urban analysis about spatial relationships. There you get more information how this whole thing works. Basically, it computes shortest distances between street segments or in between all segments in a street network. And we can have here certain outputs. What I use here is the betweenness centrality, which is computed as somehow the highest betweenness centrality is the area that is most often used by all shortest paths that are computed in the network. Anyway, that's not so important. This just creates the visualization for a centrality measure. Preview it right here. So you see here the red area, the red street segments, they are most often used if I travel from each block or from each parcel to each other parcel. So you can interpret this as the traffic intensity. So the warmer the color, the more traffic, may be pedestrian traffic or car traffic, doesn't matter in this abstract model. It's just more. Okay, but for us important is the length of the shortest paths. So in this output we collect now the distances between all our or in the output the output contains the shortest distances between all segments in my network. So if I zoom in here, you see these segments are here also the smaller parts from here to here, and here from this crossroad to this T crossing. So these are all segments in my street network, and this output returns all pairs from to the segments that I have in the network, so all the shortest distances between these segments. What do we need? We want to have the shortest distances between our parcels that we generated. So these are now the two data structures that I've mentioned that we need to combine with each other, respectively, to pick out the shortest distances of all shortest distances, which represent the distances between the parcels. How do we do this now? That's now the difficult part, where we need a C# script again with two input values. One is the distances that we computed down here. Here I've just visualized it, so it computes, for example, from street segment with the index 0 to street segment with the index 1, computes one distance measure, and the same from street segment 1 to street segment 2, another distance measure. And here in this list you find all the distances between these two pairs. So this can be any combination of street segments in this model. That's the first input. And the second input is the list of indexes. And this comes from this output here. And what I've done here is that I've collected all the indexes from these street segments that I've used to connect the parcels to the other street network, so to the real streets. So these small stubs here, these lines that goes into the parcel, they are these indexes stored here. And that's very important because now I want to know the distance from this street segment, from this segment in my street graph, in my network graph, to all the others. So maybe I can make a screenshot here and illustrate what I need. Here we have our basic setup, and for example I want to compute the distance from this parcel to this one. Then I need to go this path. That's the shortest path, and the shortest path from this to, let's say, that one is this. That's the shortest path from here to here, and the shortest path from this one to this one is then this path, for example. So all these pairs are stored in my distance list as mentioned. And now I've used the indexes of the small connecting lines to my parcels as a second input. And now I want to ask in this script to return only the pairs that computes the distances between my parcels. So as I've drawn here in this sketch, I want to know the distance, for example, from here to here. Then I need to have the index from this parcel, let's call it index 1, to this parcel with the index 2. That's what I want to get returned from this component. Okay, so to do this, let's look how the code works. So that's now really something a little bit difficult to understand. I have my two input variables, the list of indexes, the indexes of these street segments connecting the parcels, and the data tree with the pairs that holds all the shortest distances between all indexes. And now I need to filter only the indexes from each parcel to each other parcel. Therefore, we have two nested loops. The first is used as the from which plot I start, and the second loop is used for getting the indexes to which other plot I want to travel to. So the from and to addresses are stored as we A and we B. Zoom in. These are my addresses, and they are here just taken out of my index list. I iterate through the indexes. These are my indexes. Now I take the first one and compare it with all the other ones. So a pairwise comparison. And I store this as an array with two entries, which is then the path or the steps in my path, in my data tree. And here you can see I create a new path, and I use this we array, the value array, as the steps in my path, and that's stored as the variable we path. And then I just need to look into my distance data tree to find the value that is stored in this path. But first I check if the VA and VB address equals to each others, because if I want to know the distance between index 5 and index 5, then I know it's 0. I don't need to look up into my data tree. I can just say, okay, this pair has the distance 0, and the current path, that's what I've created here. I just create a data tree that has the same, so that's a new data tree. What did I want to output? And this has the same sequence as the indexes of my plots that I used here in the list. So here I just generated this current path one after the others. And the second case, if it's not the same address, so if I want to know the distance from parcel 1 to parcel 2, for example, then I ask my distance data tree that's here used as an input. And I say, okay, I want to have the branch, and now the branch is what I've created here with this V path, this one, from and to index values that I've used in my list. And I take out the first entry, because I only have one entry in this path, that's the distance value. So that's a data tree with only one entry in it. And this value, my distance value, this is what I store under the current path. So as mentioned, the same sequence as I have stored it in the list of parcels. That's now the same logic as we've used it for the grid city. We use the same list as we stored blocks, in this case parcels, and we add the current distance into this branch. And that's then my output that I created here. If we go over to the input, here again you can see my basic input for my model. That's the data, where I've just sent the data, the distance tree to this data component, which is just a placeholder for feeding in the data. And this is now the visualization of my distance data tree. So I have these many parcels, and I create a branch in my data tree to store all the distances from one individual parcel to all the others. So in each node in my tree is a list with distances to all the other parcels in the same sequence as I've stored my parcels. And with this information I can run my simulation. To use these components, as mentioned in the beginning of this course, that's a very good way to control the input to a whole part or to a separated part of your definition. In this case, that's my simulation model. And let me preview again the simulation output. Now I can start again the loop of the model, and it will run through it, 10 iterations in my case. So here you see there are no individual steps that I run through my simulation as we have been that we are used from our grid city model. That's because I've used here the fast loop components from my Anemone plugin. Here we have this fast loop start and end component, and that's here fast loop start, fast loop end. They are doing nothing else than we've done with the normal loop start and loop end, with the exception that they are faster, but therefore they don't visualize the individual steps of my loops. So if I click on it, you see I need to wait approximately 5 seconds until I will receive another output, and then it iterates 10 times through my model. And since I have a little bit of an random values in my main control components, which you already know from the last session, from the last lesson, the output looks a little bit different. But the rest of the model is exactly the same as we've used it for the grid city model. So to recapitulate, what we've done is we've just exchanged the logic for using different distances in our model. That's all we've done. We've used realistic distances in the street network between parcels and extended somehow the representation, or what we can represent with our model, to a more detailed geometrical representation.